let's take a look at complementary events now. A complementary event is analogous to a complementary set. So it's the event that is everything that is not covered by another event. So for example, if you're flipping a coin, if the event is tails, then the complement of tails would be heads. If you randomly select a student from a class and we say, what is the probability that a student is under 20 years old? Then the complement of that would be the event where the student is over 20 years old. If we, select a student and we said, what's the probability that that student is a woman? Then the complement of that event would be the student is not a woman. It's just saying then, just like we did with complementary sets, it's everything that is not covered by that event. The thing that's nice about complementary events is that if you add up the two, you should get 1. So let's think about why that's true. If we have our sample space, and we'll go back to this sort of Venn diagram idea that we had before, here's some event. So I'm going to say event E is over here on the left. Then E complement has to be everything that's not represented by E. So everything that's not represented by E, well, if I combine that with event E, it should give me the entire sample space, which would be the whole rectangle. So that's why if you take two complementary events and you look at the sum of their probabilities, you should just get 1. Or equivalently, we can say that the probability of A is going to be 1 minus the probability of A complement. And we could rewrite this, of course, to say that the probability of A complement would be 1 minus the probability of A, equivalent statements. So let's actually apply this in practice here. What's the probability of not drawing a 4? So the not is telling me that I'm looking at a complementary event. Not drawing a 4 from a standard deck of 52 playing cards. Let's hold on a moment and actually talk about a standard deck of 52 playing cards. A standard deck of 52 playing cards has 4 suits. So there are 4 suits to a deck, and the suits are, you can have hearts, which are in red, you can have diamonds, which are also red, or you can have spades, which look like kind of like upside down hearts with a little tail, or you can have clubs, and those are black. So there are 4 suits, there are 2 colors, red and black. Each suit has 13 cards. And the cards go 2, 3, 4, 5, 6, 7, 8, 9, 10. And then once you hit 10, then you get the face cards. Those are the jacks, the queens, and the kings. And at the very end, we have the ace. Technically not a face card, it doesn't have a face on it, but it is a powerful card, so we sort of group them together. So each suit consists of 1, 2, 1, 3, 1, 4, all the way up until 1 ace. So altogether, there are 13 cards per suit. There are 4 suits, and so there are 52 cards total. Every card shows up exactly once within each suit. So if we want to talk about selecting a 4 from a standard deck, there are 4 4s in the deck of cards because there is 1 4 of hearts, there's a 4 of diamonds, a 4 of spades, and a 4 of clubs. Okay, so that's sort of your basic rundown for the structure of a deck of cards. And if you want more information about that, feel free to email me, or you can probably find something online that goes a little bit. There's not a whole lot more beyond that, but if you wanted, additional information, feel free to contact me. Okay, so let's focus on the question that we have here. What is the probability of not drawing a 4 from a standard deck of 52 cards? Well, there are 2 ways that we could do this. The probability of not drawing a 4, I could approach this as a complement. This would be 1 minus the probability of A. So if I have not a 4, then basically what's the complement of the complement? That would just be the probability that I do draw a 4. So what is the probability of actually drawing a 4? That would be 4 4 out of 52 cards. Because remember, there's a 4 of hearts, a 4 of diamonds, a 4 of spades, and a 4 of clubs. So we have 4 cards total out of the 52. And so we end up with 52 out of 52 minus 4 out of 52, and this gives us 48 out of 52. And so we've found the probability that we were looking for by using the complement. It's a little bit easier to consider the probability of drawing a 4 because that's exactly one number, so one type of card that you have to consider. Whereas if you try to think about the probability of not a 4, then you have to make sure that you've covered all the cards that are not 4s. So you could approach this problem without using a complement, just directly. The probability of not getting a 4, well, there are exactly 48 cards in the deck that are not 4s. But the way to find that 48 is because I said, oh, well, there are 4 4s, so 52 minus 4 is going to give me 48 cards. So you can do this problem directly, but the arithmetic and the algebra that you're doing to solve that problem is really what the complement is just leading you through. So I would go ahead and do this with the complement, but you're more than welcome to do it with sort of directly like we've done here in the red. Let's take a look at another example of complementary events. Let's consider this next example. 4 coins are flipped. Let's find the probability that tails comes up at least once. So let's think of this. Let's see how we can phrase this. So we want the probability that tails appears at least once. Well, if I want tails to show up at least once, that means I need to see, well, how many ways can tails occur exactly once, exactly twice, exactly 3 times, and exactly 4 times. And that's a lot of different options to keep track of. So we can instead write this as a complement. So let's do 1 minus the probability of the complement of tails appearing at least once. Well, if tails is appearing at least once, then the complement would be that tails does not appear at least once. So tails does not appear at all. So this would be no tails. And so really what we're looking at is 1 minus the probability that we roll all heads, or sorry, that we flip the coins and they all land on heads. And so let's see. We have 1 minus the probability that all coins land on heads. Well, there's only one way to flip the coins and have all of them land on heads, and that's by flipping all 4 of them and exactly landing them on heads. And we need to divide it by the total number of ways, the total number of outcomes that our coin flips could have, and that would be given by 16. You can go ahead and list that out, or you can think about counting it in various ways, but you should end up with 16 ways that you can flip your coins. And so we'll end up with 16 over 16 minus 1 over 16, which will give us 15 out of 16. And that should seem fairly large, but that should seem reasonable because there's only one possible outcome out of all the possible outcomes that doesn't have a tails in it. And that's if we had all heads. Every other outcome is going to have tails in it. So we should have a fairly large probability. Alright, that's all for now. See you next time.